Hi guys, so welcome to video 4.3.3. This should say 0.3 here if you have a version that says 0.1. Okay, structural explanation of acid strength. So let's figure out, based on the structure of these compounds, why acids are as strong as they are. So if you have a highlighter, now's a good time to grab it. The strength of an acid is determined by the strength of the HX bond. So H being hydrogen, X being that negative ion. When the HX bond is weaker, H plus is more easily removed. So when the HX bond is weaker, the hydrogen ion is more easily removed. So if this bond is really weak, they're not hanging on very strongly, that means the hydrogen ion is going to be able to come off a lot easier. If it comes off easier, that means it's a stronger acid because more hydrogen ions are going to come off, resulting in a stronger acid. These explanations are often related to the electronegativity of the element, or how strongly an atom attracts an electron to itself. Note that nitrogen, oxygen, fluorine, and chlorine have the largest electronegativities among all the elements. So you'll see here some electronegativity values. So these are relative values. Fluorine is the highest electronegativity on the periodic table, so it's got a value of 4. Oxygen is second at 3.5. We have nitrogen and chlorine tying at 3. So you can see those. Please know that trend. You don't need to exactly memorize those values. It would probably be helpful to know fluorine is 4, chlorine and oxygen's numbers. You don't need to memorize all of them, but in general, there's the values. Okay, example 5. Rank each of the following from weakest to strongest acids. So the first thing we need to do here is draw the Lewis structures, or draw the chemical structures. So let's do that. So first, draw the structures. Okay, HOCl, that oxygen is in the middle, so we have a hydrogen there, an oxygen, and a chlorine. And then we have HOBr, and then HOI. Okay, so these are 3 acids. So all of them are in the form HOX. So all are HOX, X being that negative element there. Compare the electronegativities of X. If we compare the electronegativities of X, that's the only thing that's different, and so that's going to tell us the differences in these acids. So compare electronegativities of X. So let's do that. So we have chlorine, bromine, and iodine. Chlorine, bromine, and iodine would be right down here. It's not listed. So following the trend, that's going to be even lower. So the greatest electronegativity of these 3 is going to be chlorine. So chlorine's the greatest, followed by bromine, and then following the trend, even though it's not listed, iodine comes next. So chlorine, bromine, iodine. So the stronger the electronegativity of X, the stronger this electronegativity is, that means the more it pulls electrons toward itself. So away from the HO bond. So the stronger the electronegativity of X, of X, 1, the more the electron cloud misspelled that. The more the electron cloud is pulled or polarized away from the HO bond, and if that electron cloud is pulled farther away, for example, if chlorine is hogging all of the electrons that are around this whole compound here more toward itself, this HO bond is losing, it's not losing electrons, but the electrons are spending less and less time in this HO bond, which means that this bond is getting weaker. And if this bond gets weaker, that means this hydrogen's going to be able to come off easier, and that'll be a stronger acid. So the more it's pulled away from the HO bond, the stronger the acid. Due to a weaker HO bond. So let's go ahead and list these in terms of their strength. So the weakest, so I'm going to list them from weakest to strongest. So the weakest would be HOI, because it's the least electronegative. So that's going to be weaker than HOBr, which is going to be weaker than HOCl. So this is the strongest on this side. Alright, now let's look at the next set. So here, we're going to draw these again. All of them are in the form HO, and then we have HOCl, and some number of oxygens. I'm going to say N oxygens. So HOClO(N). Let's look at oxygen. Up here, oxygen is very electronegative, second only to fluorine. It's the second most electronegative element on the periodic table. So it stands to reason that if you have more oxygens, so if you have 4 oxygens versus, 2 oxygens here, you are going to be a lot more electronegative, pulling way more of those electrons away from the bond, the HO bond here, and it's going to be a stronger acid. So oxygen is very electronegative. If you have more oxygens, that leads to the electron cloud being pulled away from the HO bond. And that leads to a stronger acid. And so if we look here, the one with the, least oxygens at the end, that one is going to be the weakest. So let's go ahead and list these. HOCl, that's going to be the weakest, followed by HClO2, it's got 2 oxygens there. That one only has 1. Followed by HClO3, followed by HClO4. And that's going to be your strongest, so strongest on this side. Okay, looking at your last set, we don't have any oxygens here for the first time. We just have HF, HCl, HBr, HI. So in the previous examples, all the acids had HOX bonds. These are just HX. And since X is different with different electronegativity values, we have to look at them differently. So, while the electronegativity of fluorine is greater than chlorine and bromine and iodine, so fluorine is the greatest, the size here is actually going to have more of an impact. So, if you have a larger size, that means you're going to be farther away. So if this X is really, really big, it's going to have to be, its nucleus is going to have to be farther away than that of hydrogen. If you're HF, fluorine is very small, because remembering your trends, this is small, you get bigger as you go down, and you get bigger also as you go left. So small, a little bigger, bigger, biggest. So if you're very small, you're going to be very close to hydrogen, and you're going to be able to hold on to it very tightly because you're close. For very large, you're going to have a long bond. That bond's going to be spread apart more, and you're not going to be able to hold on to that hydrogen as strongly. So that's going to lead to a weaker acid. So, let's summarize. While the electronegativity of fluorine is greater than chlorine, which is greater than bromine, which is greater than iodine, size of F- is smaller than chloride, is smaller than bromide, is smaller than iodide. And those are all the negative ions that are associated with the hydrogens in these acids. If you have the larger the X is, so the larger size of X, we said that leads to a weaker HX bond, which a weaker bond with the hydrogen leads to a stronger acid. So the smallest one, HF, is going to be our weakest acid, followed by HCl, followed by HBr, followed by HI. So this is our strongest. And hydrofluoric, that's why hydrofluoric is a weak acid, because that fluorine is very small and it holds onto the hydrogen very, very tightly, so that hydrogen isn't going to come off very easily. Where here, the iodine is very large, so it can't hold onto the hydrogen as strongly, and that hydrogen comes off easily, making it a stronger acid. Okay, that is it for lesson 4.3 and video 4.3.3, and this is it on types of acids.